Hello everyone, and thank you for joining this session. I'm Moein Younesi Heravi from North Dakota State University, presenting our research, a framework for real-time estimation of human activity intensity in indoor environments. To set the stage, let's first ask why we should bother quantifying activity intensity. From a building operations point of view, occupants' movement drives metabolic heat. Knowing how hard someone is working lets an heating, ventilation, and air conditioning or HVAC system lower heating or raise cooling only when needed, therefore saving energy while maintaining comfort. At the same time, a continuous measure of movement intensity opens the door to non-intrusive health monitoring and ergonomic assessment. However, current approaches face at least four key challenges. One, most studies attach sensors to the body, and users often feel uncomfortable. Two, using category labels such as walking, sitting, running, and so on results in missing gradual transition in exertion. Three, many deep learning models need thousands or millions of labeled data which are costly and difficult to collect. And four, systems trained in one situation, one room, or with one group often do not perform well somewhere else. These gaps motivate the framework you will see, we propose and you will see in next slides. This study has two clear goals. Primary goal is to create a continuous and non-intrusive activity intensity score, let's call it AIS from now on, that converts ordinary video pose data into a real number, and as a result of which gives a finer view than simple activity classes. Secondary goal would be to implement and test this pipeline in control trials to confirm that AIS works in the way that is intended. With these goals in place, let me walk you through the details of the methods we used to achieve these determined objectives. Here is the big picture behind AIS. We start with video frames and run MediaPipe pose detection to extract body landmarks, 33 key joints per frame. From those landmarks, we calculate key kinematic measures, things like how fast the joint rotates or its range of motion. Finally, we combine those measures into one continuous activity intensity score that updates every second or every determined time interval. This straight line workflow keeps the system light enough for real-time use while capturing the information we need. The framework was shown in previous slide unfolds in 5 steps. In step 1, MediaPipe pinpoints 3D coordinates of the main joints in each frame. In step 2, we group landmarks into 14 meaningful body chains, such as arms, legs, torso, spine, and so on, in order to analyze motion segment by segment. In the uh, third stage, which is movement parameter extraction, for every chain, we pull 6 indicators such as angular speed and angular acceleration. What are these indicators and how these parameters are calculated from the angle between joints will be presented in the next slide. Step 4 is, in step 4, each parameter is normalized, weighted, and summed to give an AIS for that specific chain. Core dynamic, meaning speed and acceleration, get higher weights, while the other fours share the balance. In the last and fifth stage, we average the chain scores to produce one overall AIS for the whole body. It should be mentioned that any chain that camera can't see is skipped. Together, these steps turn raw video into a number that climbs smoothly as activity intensifies. This slide shows the six kinematic parameters that feed AIS. These six include angular speed, angular acceleration, range of motion or ROM, peak angular speed, movement frequency, and finally rotational energy. After normalizing each of these to 0, 1, we weight and sum them to create the chain level AIS. This mix of velocity, acceleration, amplitude, rhythm, and energy gives a balanced picture of movement intensity. Uh, okay, with the methodology covered, in the next slide I will explain how we designed the experiment to validate these choices. To test the AIS framework, we ran a controlled pilot study. Participants include 3 healthy adults. Each of these participants performed 3 distinct activities that span the intensity range of low, moderate, and high. Low intensity included activities like sitting, standing still, typing, and so on. Activities in moderate intensity were walking at a regular speed, repeated arm movement, disorganizing, and dusting. And finally, heavy exercises like jogging in place, jumping jacks, and push-ups comprised high-intensity activities. Every activity lasted 80 to 90 seconds, followed by a 1 minute rest in between. A single normal RGB camera captured video at 30 frames per second. No variable were used, so the setup matches the non-intrusive goal of the AOS. In the next 3 slides, I will show the results. This slide shows second by second AIS traces for all 3 participants. Each gray band marks the transition from low to moderate and then from moderate to high activity. Let's analyze the graph. First, as soon as the test switches, the score climbs sharply and settles into a higher band. Secondly, low, moderate, and high intensity tasks each stay at a specific range. There is very little overlap. Third observable is that even though the participants chose different activities within each band, every trace shows the same three-tier structure, which confirms that AIS is participant independent. Finally, real-time responses can be seen. The jump happens within a few frames, so the system can feed live data to a controller, dashboard, or so on. These time series plots gives or first evidence that AIS tracks movement intensity correctly. Averaging in the second graph, averaging the score for each activity level gives a more clear summary. We can conclude 3 points from this graph. First, mean AIS rises steadily from low to moderate and from moderate to high for every participant. Second, the 3 colored bars differ in height but share the same upward slope, showing that individual movement style does not break the metric. And third, the bands do not touch. Even the lowest high score is above the highest moderate. These averages reinforce the time series finding previous slide that AIS scales reliably with activity intensity. In the last slide of the results, we look inside the score. The 6 box plots on the left compare each movement parameters across intensity levels for one participant as an example case. Let's summarize what these plots show us. First of all, every component rises individually. Speed, acceleration, ROM, peak speed, frequency, and rotational energy all show higher medians and wider range as intensity goes up. Secondly, clear separation can be seen even within a single parameter like ROM. The high activity boxes sit well above the low ones. Lastly is consistent direction. No parameter behaves erratically, which means the weighting scheme we chose adds parallel signals rather than conflicting ones. Taken together, these trends provide strong support for the validity of AIS and its underlying features as sensitive indicators of movement effort. To sum up, we introduced a camera-based framework that estimates human activity intensity continuously and in real time. No variables, no fixed activity labels, and no individual calibrations. It is also necessary for us to know the limitations of our work. Two main limitations are first, when a part of body moves out of view, some landmarks are missed, as you can see in the photo. Um, and second is that using normal camera, normal video raises privacy concerns. Therefore, in the next steps, we should address these two by using a multi-camera system to cover blind spots and probably thermal cameras to address the privacy issue. We believe these improvements will move us closer to truly adaptive occupant-centered building operation. Uh, these are the key sources that guided our work. A complete reference list is included in the written manuscript. Uh, Finally, I would like to acknowledge the support of the NSF program for funding this research, and thank you for your attention. If you have any questions after the session, please feel free to reach out to us. Our contacts are listed here. Thank you.